So welcome back. We'll start a new session. So our next speaker is Hitesh. He'll be talking about depletion forces.
Hello. So I would like to thank the organizer to giving me the opportunity to speak in this Institute Seminar Day 2024. So from the title, it's Introduction to Depletion Force. It's not my topic exactly, but it's in my future prospect. So I'll just go through what's basics of it and what are the history and all, how it came about, and yeah. So what is depletion force? We should start with the definition. So it's a very basic definition you can see. I mean, so when assume two type of particle, type 1 or type 2, and let's assume the colloidal particle type 1 are dispersed in a solution in which non-adsorbing particle, that can be hard sphere polymer chain, are present, and then colloidal particles start attracting each other. As the density of non-adsorbing particle increases, this attractive force is known as depletion force. So I'll show you the cartoon. Let's assume there are two type of particle, green and the red one, and as we increase the density of type 2 particle, what will happen? Type 1 will form a cluster. The phase separation will occur. This attractive force, generally people call it depletion force. The word depletion generally means depleted from the surface of the particle. So what happens? Type 2 particle is kind of depleted from the surface of type 1. So hence the name depletion. So the idea behind is, so if you consider type 1 particle here, there is a volume there known as excluded volume, in which type 1 particle cannot enter, and because of which they surround it, the type 1 particle, and the type 2 and type 1 will have the pressure difference, osmotic pressure difference, because of which type 1 will have the attractive force. So this is very basic idea. I'll show you some visualization. So if in the picture you can see there are two type of particle, like one is colloidal, the sphere is colloidal, and there is macromolecule inside. As macromolecular density increases, we are seeing that colloidal particle are forming a cluster. So there is a video here, you can.
Daily life products such as food and paint are mixtures of colloids and polymers, such as proteins, latex particles, and polysaccharides. Exclusion of the polymer chains from the colloidal particles results in effective depletion layers. Overlap of these depletion zones induces an indirect attraction between the colloids. Above a certain polymer concentration, this leads to phase separation into a colloid-rich and a polymer-rich phase.
So there will be phase separation when the two type of particle, like density of the type 2 particle increases, is the basic point. So I'll go into the discovery of depletion force, how it come about. So it started from the 1953, where Osawa in Nagoya University organized a conference where he invited not in the physics department people, but all over the biology, chemistry, microbiology, etc., etc. And there they talked about this kind of phenomena. So what he saw was this kind of phenomena is very common in many fields. So first, for example, I'm giving some of the example. For example, in the aggregation of red blood cells in high polymer, these kind of things were known at that time as well. That as you put high polymers inside on a surface where RBC is there, the RBC will just phase separated from that. And same in water, soil powder makes a colloidal state. If some macromolecule are added to the soil particle will aggregate, and the soil will form a solid block. There are a few other examples as well. For example, in this microbiology field, the bacterial cells. So by adding macromolecule, for instance, methyl cellulose makes aggregation of swimming bacterial by kind of entanglement to their tails. So there are other examples as well. So there are, by that time, 1953 as well, people know these kind of phenomena, but there was no underlying physics or science behind it. Like people have not formulated what kind of physics it can capture. So what Osawa did, so he came with some idea to how can we explain this kind of phenomena. So he came up with the idea which based on the two basic things like osmotic pressure difference or two-phase approximation. So first was, this very basic idea. So if we consider, sorry. Yeah, so if we consider two plates in a solution of colloidal particle, when the distance between the plates become less than the diameter of the colloidal particle, they cannot enter inside the particular space, and there will be osmotic pressure difference between the two phases, because of which there will be attractive force between the two plates. And this kind of force, they call this AO theory at that time. Asakura-Osawa theory. Same, the two-phase approximation was also something of that sort. They consider macromolecule and inside a colloidal particle. So macromolecule itself, single macromolecule is also a single phase where all the monomers, interaction between the monomers give rise to a particular phase, and which is kind of related to intrinsic viscosity of the solution. And then the all individual macromolecule consists also a solution, which is kind of related, which can be governed by second virial coefficient of the solution. So this is the second idea. So what happened after the birth of air theory? Nobody talked about that much, like 1954. After that, nobody talked about that much. But in 1980, another independent group, Bridge et al., formulated the same kind of theory. But later they came to know, oh, this theory was already formulated in 1954. Thereon, people start considering that work, and after that we can see the citation start increasing exponentially. Before that, 1980, there was no citation of the particular paper. So now the recent development, we as a physicist, we want to know what kind of mathematical form this depletion force can have. So we'll start with a very basic idea. People have started with the very basic idea. Again, the same, there is excluded volume here. You can see there is, with the two particle intermediate distance, there is a distance in which this kind of particle will not enter. So the force should be proportional to that surface area or the volume, right? Then if the particle around it exerts some osmotic pressure on that, the force should be proportional to that, the density or the, you can say, osmotic pressure. So this is the very basic idea. So people try to use that, and this S gives the surface area, geometric surface area we can found. And this surface area can be, is function of kind of radius of both of the particles, type 1 and type 2. And then this pi is the osmotic pressure, and this osmotic pressure can be found by various theories. We can use very basic ideal gas that is very, like, directly proportional to the density of the Crowder. Then there are other theories like third order virial expansion can be done, or scaled particle theory. So like still it's a working phase, like people have not exactly found what could be the mathematical form. But like scaled particle theory and virial expansion has quite a matching with the simulation result as well. So in the depletion theory, there are some like universal fact people have established now, that if there are like smaller particle or bigger particle, smaller particle are better than the bigger particle for the depletion effect. So if we take like two different type of particle, radius R1 or R2, the R1, if it is less than the R2, that will be better in crowding or better in forming the phase, will be in the phase separation. So these are the like reference I'm giving. They have done this kind of work, that analysis of the size dependent macromolecule crowding shows that smaller is better and this. Then also like for bigger depletants, depletion effect is independent of size of bigger particle, but smaller ones, it also depends on the size of the smaller particle. So these are some basic things people have kind of established now. These are the references again. So if somebody wants to start to study about this kind of thing, one can go into the very first paper, that is in 1954 by Osawa himself in JCP, and then these are very recent some paper, the discovery of depletion force, and then this paper is really nice. I mean, it has all the references of the work which has been done from 1954 to 2021 recently. All the references are there. What kind of experiments, what kind of simulations, what kind of theory people have developed to study these kind of things. So this paper is also by Osawa himself in 2021, before like in 2 years back. So here also he mentioned the history and how he came up with the idea. So with this, I would like to acknowledge my supervisor, Professor Satyavani and Rajesh. Thanks.
Thanks a lot for this beautiful talk. Are there questions? Okay, if there are no questions, then we'll thank the speaker again. Oh, this is Anup. Okay, good. So Anup is our next speaker. So start now.
This will work, right? Okay, so good afternoon everyone. I am grateful to Amri and all the organizers for inviting me to speak here. Now I am going to talk about one of the most famous problems in mathematics and number theory, the Riemann hypothesis, which somehow very mysteriously appears in unexpected places in mathematics, and it's my intention to make you understand how important and why this problem is so important. Okay. So in number theory we study numbers, and numbers can be factorized into primes. So primes can be thought of as the building blocks of all the numbers. For natural numbers we know that every number can be uniquely factorized into primes. So if I want to study primes, this is one of the functions which is an extremely important function for us called the Riemann zeta function, which is given by this series summation 1 over n to the s. This series is convergent for complex numbers lying in this half plane, real part of s greater than 1, and in this half plane it also has this Euler product or product over these primes of this 1 minus 1 over p to the s inverse, and this equality is nothing but equivalent to saying that all natural numbers can be uniquely factorized into prime numbers. Now notice that when if I take s as 1, I mean going very close to 1, then we get a divergent series, harmonic series over here, that immediately tells me that this product should be an infinite product. So it immediately gives me infinitude of primes, otherwise this would be, this goes to infinity, so this must also go to infinity. Now if this goes to infinity when s equals to 1, that also tells me that summation 1 over p, where p runs over prime numbers, should also go to infinity. This immediately tells me that there are more primes than any geometric progression on natural numbers. So just by staring at it without doing any work, we get something about the distribution of primes. But this is also a function which is defined on complex numbers, so complex plane, and it has some really nice properties. The first one is that although the series definition only works for the right half plane, real part of s greater than 1, this can be analytically continued to the whole complex plane except for a pole at s equals to 1, and after you do this continuation, there is some peculiar relation between the values that the function takes at s and 1 minus s. Let us try to look at it in a more pictorial way. So this is the complex plane, and here is the right half of the plane. Here the function is given by this series, which is also the same as this product, but that only happens in this particular half plane. But this function has a analytic continuation to the whole complex plane, and because of complex analysis this is unique, and the values it takes at s and 1 minus s are related. Now in this half plane, because it is a product, it is non-zero. So therefore we kind of understand what happens to the function in this half plane, which is left of sigma equals to 0. Mysterious region is this strip between 0 and 1. Now Riemann himself computed some of the zeros in this region, and he noticed that all the zeros seem to be lying on the half line, and then he hypothesized that all the zeros in this particular strip, there are infinitely many of them, all of them should lie on the half line. That is what we call the Riemann hypothesis. Okay, so all this is very well and good, but why is it so important, and what do Riemann hypotheses imply in general? So first is, of course, we started with zeta function because we were interested in understanding distribution of primes. So Riemann hypothesis should tell us something about primes. So suppose pi of x be the prime counting function which counts the number of primes up to x. Then one of the major discoveries of 19th century, towards the end of 19th century, is the prime number theorem. Again, by studying properties of zeta function, they proved that this pi of x is given by this integral, which is approximately x by log x, and this plus this error term. But if you assume Riemann hypothesis, you get something much better. This error term becomes really good. So this is one of the first applications. Now moreover, if I want to know about how far are two consecutive primes, if you look at two consecutive, how far they can be. So there is a conjecture of Legendre which says that if I look at any two consecutive squares, there has to be a prime between them. So in other words, two consecutive primes should be separated at most by square root of that number, prime number itself. Under Riemann hypothesis, Kramer in 1919 showed something which is much close to Legendre's conjecture, but not quite there. So he says the difference between consecutive primes, pk stands for the kth prime, is at most square root of pk, but up to some log pk. So this is almost there. And the actual expected thing is much smaller than this, but let's not get into that. So we got some information about gaps between primes, again under the Riemann hypothesis. But here is another very curious thing that Riemann hypothesis implies. So this is a story of prime races. So if I look at arithmetic progressions, we would expect any arithmetic progression where the first term and the common difference are co-prime should have infinitely many primes. Furthermore, it should be uniformly distributed across arithmetic progressions. What does that mean? If I start with any a and m which are co-prime, then a mod m, the set of, that's an arithmetic progression. The number of primes in this arithmetic progression will be the total number of primes up to x divided by the total number of congruence classes, which is congruence classes, which is phi of m. So in other words, let's look at an example. If I look at 1 modulo 4 and 3 modulo 4, we expect asymptotically both the classes to have exactly the same number of primes, asymptotically. But when we try to actually count the number of primes, which are 3 mod 4 and which are 1 mod 4, we notice that the number of primes in 3 mod 4 is always greater than the number of primes which is 1 mod 4. So this is what is called Chebyshev bias. And in the beginning of 20th century, under the generalized Riemann hypothesis, when I say generalized Riemann hypothesis, it means Riemann hypothesis for some other functions, not the Riemann zeta functions, but similar to Riemann zeta function, assuming that all the zeros lie on the half line. So then a generalized Riemann hypothesis, which we will call GRH from now on, implies a Chebyshev conjecture. So this is a really curious conjecture, but Riemann hypothesis helps us in proving such a thing. Okay. So now we go to another problem which is also of interest to computer scientists, which is primality testing. Given an integer n, you want to figure out whether it is a prime number or not, but in a good amount of time, in optimal time. So in this context, we kind of know the AKS Agarwal, Kayal, Saxena proved the famous theorem in 2002 that the primality testing can be done in polynomial time. However, long before that, the generalized Riemann hypothesis in fact implied that this can be done in polynomial time. So this is one of the examples where Riemann hypothesis had already implied something which was proved using, which took a long time to be proved unconditionally. Okay, now here is another problem again which has, which Riemann hypothesis has some impact, which is the famous question of Goldbach, which says that for any even number greater than 2, can be written as sum of 2 primes. Let's ask a slightly easier question, which is called odd Goldbach and is implied by the original Goldbach conjecture, which is that every odd number greater than 7 can be written as sum of 3 primes. For example, if you take 9, it is 5 plus 2 plus 2, take 11, it is 3 plus 5, and so on. Now it was shown by Hardy and Littlewood 1923 that under generalized Riemann hypothesis, this odd Goldbach is true for sufficiently large n. And after a few years, Vinogradov, using some average version of Riemann hypothesis, was able to prove this statement without using GRH. And more recently, Desoué, Effinger, Terriel, and Genoviev in 97 proved that this odd Goldbach is true for all numbers greater than 7 under GRH. And with some really groundbreaking work of 21st century, finally this odd Goldbach conjecture is settled by Harold Helfgott. Okay, so here is again another example where GRH had already told you something is true, and it took more sophisticated techniques and time to get the theorem unconditionally. And finally, we come to an application which is my favorite application of Riemann hypothesis. This is the study of unique factorization. Now, what is unique factorization? Not all rings that you see in your daily life has unique factorization. For example, 1 plus square root minus 5, 1 minus square root minus 5 is 6, which also can be written as 2 times 3, which in other words tells you that this type of a ring is, although it looks similar to integers, it doesn't have unique factorization. However, think rings such as z root minus 1, z root 2, they all have unique factorization. Now, there is a constant which is called the class number, which captures how far your ring is from having unique factorization. If class number is 1, that means it has unique factorization as for these things, and if it is greater than 1, then the larger it is, the farther you are from having unique factorization. So, in this context, Gauss made a conjecture that if d goes to negative infinity, then the class number goes to infinity. Okay, so that's the story, but where does Riemann hypothesis come in? This is one of the very curious phenomena that happens. It was proved by Gronwall in the beginning of 20th century that generalized Riemann hypothesis implies Gauss's conjecture. 20 years later, Doering and Mordell showed that if Riemann hypothesis is false for just the Riemann zeta function, then also we get Gauss's conjecture. And then soon after, it was shown by Heilbronn that if generalized Riemann hypothesis is false for any of those L functions for which we have for any of those L functions assumed in Gronwall's work, then Gauss's conjecture holds. So, in other words, Riemann hypothesis is true implies Gauss's conjecture. Riemann hypothesis is false also implies Gauss's conjecture. Therefore, Gauss's conjecture should be true. So, this is one of the really curious examples of this. And I'll end by giving some honorable mentions, which I don't have time to talk about. Chawla problem, smallest prime in arithmetic progression, Artin's primitive root conjecture. We know this is true under generalized Riemann hypothesis. Generalized Brouwer-Siegel conjecture, again true under Riemann hypothesis. Andreev conjecture, which has very recently been resolved, but some time ago we knew that it is true under Riemann hypothesis. Well, thanks a lot. Hopefully that has inspired you to study Riemann hypothesis.
Thank you, Anu, for this very nice talk. Do we have questions?
A very nice talk, thanks. Quick question about the proof of the polynomial time primality.
Yes.
So Agarwal Kyle Saxena gave an algorithm. Did the earlier person give an algorithm that works?
Okay. He gave an algorithm, but he kind of assumed that primes are, he assumed how well distributed primes are. You don't have to look for too much to find a prime. That kind of a statement will be implied by Riemann hypothesis. Practically speaking, it should work because this we would hope for Riemann hypothesis to be true. Yeah. No. It's no. I don't think so. No. They give an interval in which you kind of look for. Okay, maybe I don't know it properly, but I thought that was what was being used. It's yeah.
Okay.
Yeah. When you say undecidable, that may very well be true. we don't know, right? Oh no, we don't prove it. We just say that if Riemann hypothesis is true, then this is true. That's all the statement is. Yeah.
The same statement you also said that Riemann hypothesis.
Yeah. Correct. Yeah.
Since it's either true or false,
Yeah. Therefore, this correct. Oh, that you have a issue. Okay, no. Okay, so why should that be? Yeah.
So I don't know whether the Riemann hypothesis is true or false. I can't decide.
Yeah, but it should either be true or false. The state. Oh, why? Because the statement is saying all the zeros are on the half line. So it is either on the half line or it is zeros. Yeah, but if it fails.
But if it's not disprovable, it must be true.
No, I think there is a confusion about provable except undecidable things. So I'm just saying the statement is true. If it fails at some point, then also our theorem is true. So so therefore it is true. Yes.
running out of time. Okay, let's thank Anup again. So we have our next speaker as Amit Suthar. So he will talk about things that I don't quite understand. So.
Yeah, can you hear me? Okay. All right, so I'm Amit, and today I'll talk about on-shell methods in geometry of scattering amplitudes. Even though the title looks too technical, I assure you that the talk is going to be non-technical, and I'll gloss over all the technicalities, so experts in the audience, please pardon me. And I've made sure that all the, wherever there is a bit of jargon, I've marked it as a purple color, so you can just tune it out if you don't care about high energy physics. Yeah, so what is scattering? So, well, moving things collide and deviate from their original path, and that's scattering. So for instance, billiard balls, they move, they collide, and they deviate from their natural path, so that is scattering. Or someone throwing a rock at me, so that will be an example of a scattering process, okay? So what does it mean to solve a scattering process? So in simple classical mechanics, we'll solve for the outcoming momenta and using the momentum conservation and Newton's laws, and that will solve the scattering process for us. But nature is quantum mechanical, and in quantum mechanics, we can't solve for outgoing momenta. So that means we can only talk about probabilities. So amplitude, or a scattering amplitude, that squared gives us the probability for that particular outcome to happen, okay? So for instance, if we have two electrons with momenta P1 and P2, and they scatter off each other, so the probability that they come out with momenta P3 and P4 is the mod square of this quantity that we are going to talk about here. So how do we calculate these scattering amplitudes? So quantum field theory is the usual way to do it, and what we do is we calculate correlation functions. Okay, so so in quantum field theory, particles are merely excitations of the quantum fields, okay? And you have, for instance, this phi field can be said to describe the electron field. And if that is the case, then we find such 4-point correlation functions, and the one particle pole of this correlation function will compute the 4-particle amplitude for us, okay? And yeah, so for instance here, if we take appropriate poles and residues of this guy, we'll get the 4-particle amplitude here. All right, yeah, so one of the key concepts in QFT is the presence of virtual particles or off-shell particles. So that means that their energy squared is not equal to momentum squared plus mass squared, okay? And they act as the messenger for interaction. So for instance, electromagnetism is mediated by photons, okay? So we draw these kind of diagrams and we compute these. These diagrams are called Feynman diagrams. You might have seen them here and there. And yeah, so that is how one would usually compute amplitudes. So today I'm going to talk about strong nuclear forces. So that is one of the 4 fundamental forces, and QCD, quantum chromodynamics, dictate the dynamics of the strong nuclear forces. So just like photons are the mediators for electromagnetism, gluons are the mediator for strong nuclear forces. And now let's say that I want to calculate a 4-gluon amplitude, okay? So I'll draw just like this. I'll draw all the diagrams that can contribute to something like this, and that is 4 such diagrams, okay? And after doing some calculation, what gets an answer like this, okay? So here notice that just like photon has 2 polarizations, you know, the usual polarizations like circularly polarized light and all. So gluons also have polarizations plus and minus. So for this particular polarization configuration, we get this answer, okay, where these symbols mean this. So you take momenta P1 and you dot it with the P2, and then you get this angle bracket thing. These are called spinor helicity variables. We don't need to worry about them, yeah. So now this was a 4-particle amplitude, and now if I want to calculate higher point amplitudes, let's say 2 to 3, 2 to 4, and so on. So the number of diagrams that contribute to process keeps increasing. So for instance, if you have this process, then you'll have some 25 diagrams and 220 diagrams and so on. And these are not just for academic purposes. Like these are used in actual collider physics and all. So people do care about how to calculate them efficiently. So for instance, if you want to calculate 2 gluons going into 8 gluons, the number of such diagrams will be more than 1 million, and all of them individually will be very complicated to calculate. Okay, you wouldn't actually sit down and calculate each one of them. So this was 2 to 2 amplitude. So now next, if we add up these 25 such diagrams, the answer actually turns out to be this. Okay, it's neat and simple. And what happens is that for any number of external legs, the answer is just this. So even if you have million, billion diagrams, they just somehow add up, and the answer is just simple, neat expression like this. So this is very unexpected, and the usual QFT will not know why that is happening. So that means there is some underlying hidden structure or something that the usual Feynman diagram techniques is missing. Okay, so why are the amplitudes simple, and there should be a simpler way to actually calculate them. So the inefficient way is inefficient because the action principle has redundancy due to field redefinition and the choice of gauge and so on. Okay, so but a scattering amplitude is independent of all of them. Okay, so to bypass this, what we do is something called on-shell methods. That means you use lower point amplitudes to build up higher point amplitudes as a recursion. All right. So this is based on the idea of factorization, that you take 4-point amplitude, let's say, and if you take a particular residue of it, then it decomposes into a 3-point amplitude and 3-point amplitude. Okay. So a systematic way to do this is called BCFW, and that's a vast subject on its own now. Yeah. So now let's move on and look at a more complicated amplitude. Okay. So if we flip one of the polarizations, so for instance, this one we saw if all of them are plus, 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 plus. Okay. But if we flip one of them, we get horrible expression like this or this. So now this, these two are supposed to be equal, but they don't look like it. And now can we ask, like, why do they look so different, or is there something more to it? Like, is it just a bunch of algebra, or is there something more to it? So what happens is that something very neat and very surprising, like nobody expected it, but this amplitude, this answer, and this answer is actually volume of a 3-dimensional object, this one. So I'm not oversimplifying it in any way. So this amplitude actually is volume of a polytope in CP3. So actually this term corresponds to the volume of this tetrahedron. And imagine this tetrahedron and chop off its top, that is this small little thing. So then if you take the difference of the volumes of 2 tetrahedron, you get the volume of this shape. Okay, and you can also triangulate this shape into 3 tetrahedrons in a different way. Okay, so you can convince yourself that there are different triangulations possible for this polytope, and actually these different looking representations are merely different triangulations of the same polytope. Okay, so this is very surprising and unexpected, and actually it led to a whole lot of more things in later on. So what happens is a higher point amplitude correspond to volumes of polytopes with higher number of faces. So for instance, 6-point correspond to a polytope with 5 faces. So 5-point amplitude correspond to volume of polytope that has 4 faces, that's a tetrahedron, and so on and so forth. Okay, that is very unexpected, and yeah, and technically these polytopes live in CP3 spaces, and these are the coordinates are momentum twisters and so on. And this is a well-known result since I think 10 years now, and what we are trying to do is do something for massive particles. Yeah. So the simple nature of Park-Taylor amplitude, this one is called Park-Taylor, and this polytope picture, sorry. So this is due to the underlying conformal symmetry of this Yang-Mills theory, that is QCD at tree level. Okay, and the full quantum theory does not have such a symmetry, and the only reason that such nice properties are there for Yang-Mills is because at tree level, the usual gluon theory is actually same as this n is equal to 4 super Yang-Mills. That's maximum number of supersymmetry that you can put on a Yang-Mills theory. Okay, and this n is equal to 4 super Yang-Mills is special in many ways. It has a lot of symmetries. It is termed as the simplest QFT, and it is a low energy effective theory of a string theory, and so on. So this polytope picture, such things actually led to this was a precursor to the amplituhedron in this n is equal to 4 super Yang-Mills, where you can write all the loop amplitudes and everything as volume of some nice polytopes and geometric pictures and everything. And about what we are trying to do is we're trying to calculate some amplitudes in this n is equal to 4 theory in some massive phase. And that's it. Thank you.
For the beautiful talk. So any questions?
So these actually need conformal symmetries, right? So what happens if you have a strongly interacting theory but you're near a phase transitions? Can you calculate like different kind of free energies or something using these techniques?
I think the questions that we are asking here are in perturbative theory because we calculate scattering amplitude, and if you are near a phase transition or something, then
But if you use only the CFT as
Yes.
the underlying principle,
Yes.
whether that helps
yeah.
in calculating?
Yes, I think people must have studied n is equal to 4 planar as a CFT, and they would have calculated a whole lot of quantities.
What
which
about
I'm-
in normal quantum field theories,
normal quantum field theory? As
near
in,
phase transitions?
I don't think I'm aware of a lot of literature in that area, sorry. Yeah.
Thanks.
Okay, if you don't have any more questions, we'll move on to the next speaker. Before that, we'll just thank. So our next speaker is Smruti Dikshit. She'll be talking about transcriptional logic.
Hi. So I'm Smriti. I'm part of the Combio department and I'm working with Sandeep. So my work involves finding out how moving out of equilibrium helps cells, especially in terms of transcription. So cells are the basic units of life and they perform a variety of functions, and they do this using specialized molecules called proteins. So cells make proteins through two processes, transcription and translation. So what we have is a stretch of DNA which acts as a template. Then the process of transcription creates an mRNA out of that template, and the process of translation converts that mRNA into protein. So there are two main processes out here, but one catch out here is that all the cells in our body have the same DNA, but they clearly have very different functions and they create different proteins. So the question is, how do cells know when they need to make a protein and when they should not? So this kind of regulation can happen at many levels, but the most prominent one is at the level of transcription. So transcription, this is a brief idea of how transcription works. So you have this strand, which is the DNA. You have the green part out there, which is the gene that turns into mRNA and creates the protein. And near the gene, you have this blue region called the promoter. So this promoter is a stretch of DNA that can bind molecules called transcription factors. So there would be an empty gene, a few transcription factors would come and sit on the promoter, and then the cell would decide whether or not to express that gene. So these transcription factors are of two broad types. They are either activating or repressing in nature. So for an activator, as you increase the concentration of an activator, transcription goes up, you get more mRNA. Meanwhile, if you have a repressor and if you increase its concentration, transcription goes down and you have less mRNA. Yeah. So this is kind of like a molecular computer where this promoter region senses its surroundings, senses what type of transcription factors are present and how much concentration they are present in, and then decides whether or not to activate the gene. So yeah, and to begin studying this, we can look at a gene that has two transcription factor binding sites. So this is a simple diagram of a promoter, and it has two binding sites, the red and the brown one, and they can bind transcription factor A and B respectively. So this promoter can exist in 4 states. So 1 where there is nothing bound, 2 where only A is bound, 4 where only B is bound, and 3 when you have both bound. And you can calculate the probability of finding the promoter in any one of these states using StatMech. And to finally connect it with the transcriptional output or the mRNA, each of these states has a certain rate at which mRNA is produced, and there's a rate at which mRNA is degraded. And you have this equation out here that tells you how much mRNA you can expect, where these PIs are the probability of finding the promoter in any one of these states. So these kind of thermodynamic models have been widely used to gain a lot of insight into how bacterial transcription works, and they've been very successful in helping us create logic gates, engineer synthetic ones, and they were extremely helpful. But one thing that's important is that life requires energy. And recently there were a lot of papers that came out, and turns out that the equilibrium framework doesn't work so well in higher organisms. So there is a need to kind of understand how cells are using this energy, and how moving out of equilibrium may or may not help them in certain ways. So the focus of my work is how would cells make decisions out of equilibrium. And in particular, I'm interested in decisions in the form of logical gates or logical operations. So we can extend the same model that I showed you earlier into a more general form, where you have the same 4 states, and these states can now transition between each other. So you have these clockwise transitions denoted by the blue arrows, and the anti-clockwise transitions denoted by the red arrows. And when this relation between the rates holds, you satisfy something called the Kolmogorov criterion. And what this basically says is that if the rates are related in such a way, then this system is operating at equilibrium. And if this condition is not satisfied, that means the system is operating out of equilibrium. And since it's out of equilibrium, you need to put in some energy to sustain that kind of steady state it has. So that energy is given by that formula for delta mu, the chemical potential. So as before, the mRNA can be connected to these PIs, the probability of finding the promoter in each of these states. And since Ri and gamma are not dependent on these rates or the concentrations, we can only look at PI and get a good idea of how the mRNA production will look like. So this is an example of a occupancy profile and equilibrium. So out here you have these promoter states, the empty state, only A bound, both bound, and so on. X-axis you have the concentration of A, y-axis you have the concentration of B, and the intensity tells you the probability of the promoter being in that state. So for example, when both A and B are very low in concentration, you have a very high probability of being in the empty state. These profiles for equilibrium are always monotonic with respect to A as well as B. But when you move on and kind of move out of equilibrium, what you'll notice is that these occupancy profiles can look non-monotonic. And this has interesting implications. So for example, we'll take this profile, and now we'll look at the mRNA production. So if we assume that A and B are activators, and that this state is not active because there's nothing bound to it, and these 3 states are active, then we get an mRNA profile that looks like this when you have concentration of B and concentration of A. This is also non-monotonic. And if you kind of, if you look at the mRNA production along this blue line, you see this curve. So basically, this protein A, which is supposed to be an activator, is acting as a repressor within this interval. So it's changing its regulatory role. So this was interesting, but there were constraints to this. For A to alter its regulatory role, you need this cycle to be biased anti-clockwise, whereas for B, you need this cycle to be biased clockwise. So these conditions are contradictory, so you can't have alteration of regulatory roles for both proteins. And this has some consequences in the kind of gates you can and cannot make. So moving on to the logic gates, now that we have studied the occupancies and understood how the mRNA profile can be deduced using them, we found out that we were able to recreate NAND, NOR, OR, and AND gates out of equilibrium as well. But one interesting consequence of this non-monotonic behavior is that we get the emergence of 2 different logic gates. So this is the implication logic, this is A implies B, and this is the negation, which we've called the lack logic. So these rely on the non-monotonicity of this of the mRNA level with one of the transcription factors. Because if you wanted to create this gate at equilibrium, you would have to have an activator and a repressor. But out of equilibrium, the nature of the protein itself doesn't matter. So a consequence of the constraints about the non-monotonicity, since this alteration of regulatory role is mutually exclusive, we can't get gates such as XOR and equivalent. So this is the truth table for XOR. It is high when the inputs are mismatched. And you can imagine that to create a gate like this, we would need an mRNA profile to look like this. But this wouldn't be possible, right? Because it's because you have alteration of A as well as B. So yeah, so that brings me to the end of my talk. So to conclude, out of equilibrium, the transcription factors can alter their regulatory roles in a mutually exclusive manner. And that once, as a consequence of this alteration of regulatory roles, we are able to obtain two logic gates that can't be obtained very easily in equilibrium. And basically, you can use energy and create different kinds of logic operations, which would help the cell make different kinds of decisions. So I'd like to thank Dr. Sandeep Chaubey and my collaborator, Dr. Taya Middlecoop. He's based in the Czech Republic. And yeah, thank you.
Okay, thank you very much. Yeah. Any questions? Okay.
Hi, nice talk. So you said this XOR gate can't be, I mean, you can't reproduce the XOR logic with this construct or with this motif. So is it like you have seen other kind of motifs where, I mean, try to see whether other kind of motifs can give you this kind of XOR logic? Or is it something to relate, like the constraint is on the motif? Like that you have chosen?
So this is a very common motif that is used, but if you try to make it a little more complicated, then you could see XOR, like if you connect it to other cycles. But XOR is, they can be a little tough to make, and with this motif it can't be made. I don't know about the others, maybe.
Okay.
Hi, nice talk. So I wanted to ask, is there a possibility that you have a state with incorrect binding? Like, or is it not allowed at all?
In this case, we haven't accounted for state with incorrect binding. It's a very minimal model, but yeah, I mean, in this case, it's not.
So I wanted to also, like, if you have an state with an incorrect binding, so the question is, even within that equilibrium picture, then would you see non-monotonicity?
No, I doubt it, because if we can somehow write the partition function for this, and if we won't get any kind of concentration square dependence anywhere, so it'll all be linear upon linear.
Okay.
So I doubt it.
Okay. Yeah.
Thank you. So let's thank Smriti again. The next speaker. Okay, it's Abhimanyu.
Hello, I'm audible. I'm going to talk about a basic introduction to quantified Boolean formulas, what they mean, and just give a basic overview. So I'll start. So Boolean variables and logical operations, what I'll need, so I'll define. So a Boolean variable is just any variable which can take 0 or 1 values. So x is a Boolean variable, x equal to 0 or x equal to 1, these are the only two values allowed. And if the first logical operation is when I say x bar, I mean not of x, which is basically I say x bar is true if x is 0 and x bar is false if x is 1. The second is x or y. So x or y is true if either x or y or both are true, and it's true or 1 and 0 or false, and if x or y is false if both are 0. And x and y means x and y is true if both x and y are both true, and it's false if even one of them is 0. So this is basically x bar, x or y and x and y are the three basic logic operations I'm going to use. And I'm going to use them to define a Boolean formula in CNF. CNF is basically giving a structure, it's called conjunctive normal form. It's just basically giving a structure to my formula, and I'll explain what the structure to my Boolean formula is. So I'll define something called a clause. So a clause is basically just an OR of literals. What do I mean by literal? So every variable can either appear as either as x or as x bar. So these are my two options for a variable appearing, and so I call this a literal. X and x bar are my two literals for a given variable, and a clause is basically just an OR of literals. So x or y or z bar, this is a clause, but if I say x or y and z bar, this is not a clause. So, and I say a formula is in CNF if I have an AND of clauses. So x or y, y bar or z bar, x bar or z. These are three clauses, and I have an AND of these three, so this is just a basic Boolean formula in CNF. So given a formula, what am I interested in? I am interested in whether my formula is satisfiable or not. What do I mean by this? Is this formula satisfiable? Is there any assignment to my variables x and y such that when I plug in the assignment to my formula, this formula evaluates to true? So the question I am asking is, does there exist an x and a y such that x or y and x bar or y bar is true? The answer is yes. Why is that? Because say I have x equal to 1 and y equal to 0. So x equal to 1, the first clause x or y becomes true, and if I y equal to 0 tells me x bar or y bar is also true. So true and true gives me true. But suppose I have this formula, there exists x and we have these four clauses. I am saying this formula is not satisfiable. We can do a quick check to say why. Because say x, y, we can say we have two variables, so we have four possible assignments 0, 0, 1, 1, 1, 0, 0, 1. So if I have 0, 0, then x or y becomes 0. So 0 and anything is always false. If I have 1, 1, then the second clause becomes 0. So again, if I have 0, 1, the third clause becomes true. And if I have 1, 0, the fourth clause becomes false. So for all possible assignments, this formula always evaluates to false. So there is no assignment such that this formula becomes true. So this formula is unsatisfiable. So a way to look at this is, we say in the CNF formula, a formula is true if given an assignment, a formula is true if and only if the assignment makes all my clauses to be true. Because even if one clause becomes false for my assignment, the entire formula, because 0 and anything is always false, my formula will become false. And a clause is true if just one literal or just one variable in my clause is true, then my clause becomes true. So basically, given an assignment, a formula is true if there is at least one literal in every clause that is true. So this is the notion of satisfiability of a formula. So now moving to quantified Boolean formulas. What is quantified? So now a quantified Boolean formula is basically just a formula plus a quantifier prefix. What do I mean by a quantifier prefix? Earlier there was just there exists. Now we have the notion of for all. So we have two possible options, and for each variable in my formula I assign it either to be there exists or to be for all. So I ask the question, there exists x, for all y is x or y and x bar or y bar. So now the question is not satisfiability anymore. The question is this formula true or false? That is the notion of my question. So here is looking at an example. If I say there exists x from the previous slide, I say that this formula is false. Why? If I look at x equal to 0, then for y equal to 0, my formula becomes false. And for x equal to 1, again for y equal to 1, the formula is false. So there does not exist any x such that for all y's my formula becomes true. Therefore this is a false formula. But again, if I just do something different, I have for all y there exists x and the same formula. This formula becomes true. Why is that? Because if I say y equal to 0 and then x equal to 1, then this formula is true. Y equal to 1, x equal to 0 again makes this true. So for every y, there is some x which makes my formula true. So this is a true formula. So given we are interested in true and false, whether a QBF is true or false, one important thing to notice is in satisfiability, just the formula is important. There is no notion of ordering, but the order in which I present my variables in a QBF is very important. Not just the quantifier, but also the order in which they are is something which is very important in deciding whether a formula is true or false. How can we look at that? So one way of understanding QBFs better is looking at it as a two-player game. So what is this two-player game? We have two players. We say the existential player and a universal player. What does the existential player do? He assigns values to the existential variables. The universal player assigns values to the universal variables. How do they do so? They do so in the order in which they appear in the prefix. The game ends when all the variables have been assigned a value. So let's look at a run of how a game can proceed. Suppose the existential player will first have to play x. Suppose they play x equal to 0. The universal player will choose u. They choose u to be 0, and the existential player chooses t to be 0. What happens is that the first clause, given this assignment of x equal to 0, u equal to 0, t equal to 0, the first clause becomes 0. So the formula on this particular assignment evaluates to false. So I say that the universal player wins the game. And a different run of the game can look at x equal to 0, u equal to 1, and t equal to 0. In this assignment, all three clauses are satisfied. The formula evaluates to true. So I say the existential player wins this round of a game. A quick third round will show that on this assignment, the universal player wins the game again. So if you observe carefully, again as to why the order is important, we say u equal to x is a winning strategy for the universal player. Why is that so? Because the universal player u will always choose his value after x. Whenever u and x are the same, we can say that either x and u are both true or both false. So accordingly, either t must be true. And the third clause tells me t bar must be true for the existential player to win. So in this case, u equal to x, if the universal player plays like this, the formula will always be false. So this is what I say as a winning strategy. And if you look at it effectively, the goal of the existential player on this game is he is trying to satisfy the formula. The universal player is trying to falsify the formula. And the notion of true and false can be equated to a strategy on winning the game. A QBF is true if the existential player has a winning strategy, and a QBF is false if and only if the universal player has a winning strategy. So this is how we can, a notion of extending in true or false in general to a game or a strategy on a two-player game or a strategy. So going back, so this was basically QBF. So going back to basic satisfiability that we saw, we said that this formula was unsatisfiable. So why was it so? A basic idea of this formula or any other formula, an easy way is to look at the entire truth table. To give satisfiability, any one assignment which satisfies the formula is enough to say that the formula is satisfiable, but a single assignment which falsifies the formula is not good enough to say that my formula is unsatisfiable. I must show that there is no assignment which satisfies. So a truth table is a basic way where I list out all assignments and show that on every assignment my formula is false, so the formula is unsatisfiable. But is there a better way? So what we are trying to show is that there is no assignment such that we can satisfy the formula. To do that, there is a rule which we call the resolution rule. What does this say? Suppose I have a clause a1 up to ak or x in my formula, and I have a second clause b1 up to bl and x bar. What I can do is I can resolve them to get all the a's and all the b's and throw away x and x bar, and I say that I can add this new derived clause to my formula in a manner that if my original formula was true, adding this resolved or derived clause to my formula is still satisfiable. Why is that so? Because suppose if I look at the two clauses in the antecedents, if there is any assignment which satisfies both of them, it must be that one of the a's or one of the b's is true, because no assignment can have both x as 0 and x as 1. I am allowed to choose only one value of x. So either one of the A's or one of the B's. One of them must be 1 if there is an assignment which satisfies my formula. So that same assignment will also satisfy my derived clause, because that same A, B will again set my resolvent or my derived clause to 1, and therefore my formula will still be satisfiable. So doing this, I can add a new clause to my formula while maintaining satisfiability. And when do I say that my formula is ended? So we have this notion of an empty clause. What does it mean? This clause has no literals. So we say that there is no assignment which can satisfy this clause. So from that we say, if we can derive this empty clause using resolution, this means that the initial formula was unsatisfiable. Why is this so? Because we have always mentioned that if my antecedents were satisfiable, my resolvent has been is also satisfiable. So since this resolvent cannot be satisfied, my initial formulas was also unsatisfiable. So this is the notion, and given that this is a resolution proof on how we can show that my formula was unsatisfiable, we take the first and the third clauses, the y goes away, I take x, I add it to my formula. Then I take the second and the fourth, I can get x bar, I can add the same to my formula, and using x and x bar, I get empty. So I add empty to my formula, and once I have empty inside my formula, I say my formula is unsatisfiable, so my initial formula was also unsatisfiable. So this is one of the basic proof systems, we call the resolution of basic proof system, to show why a formula is unsatisfiable. It's a proof of unsatisfiability. So based on this, just proof systems are also not enough. We have what are algorithms. So CDCL is one of the many algorithms. How this proceeds is that it tries to construct a satisfying assignment. I'm trying to prove either my formula is satisfiable or unsatisfiable. I try to find a satisfying assignment. Suppose I find a satisfying assignment, I'm done. But in case I'm not, I fail and I create some unsatisfying assignment. This unsatisfying assignment happened because I falsified some clause in my formula. From this, I learned something new. What this learning new thing does is it prunes my search space. Initially, from my 2 raised to power n potential assignments, I have pruned my search space, and I keep going until I hit either a satisfying assignment or I generate a proof of unsatisfiability. I'll skip over how to find, and this is how in general I've suppose trail 1 and trail 2 are my 2 tries of how the algorithm is proceeding. It fails. From its failure, it learns something and it keeps going, and ultimately it fails by learning or extracting a resolution proof of the empty clause. So this is basically from a run of the algorithm, I can derive either a satisfying assignment or a resolution proof which falsifies my formula. So what we want to basically do, this is the basic idea of how it works in proposition. When moving to QBF, the notion becomes slightly more complicated. Resolution is drifted to a different proof system called Q resolution. CDCL, the algorithm extends to something called a QCDCL, which again determines truth or falsity. And what we work on basically, again, because QBFs must respect the order, we try to see somehow, which puts a lot of restrictions on how the algorithms can proceed. So we try to see if somehow the order can be relaxed in some manner, and how relaxing the order in different ways affects the strength of my proof system and the strength of the algorithm, and how fast I can prove true or false. So this is the kind of idea behind doing QBFs. So thank you.
Thanks a lot, Abhimanyu. So we have time for one question. Okay, so if you don't have any questions, we'll end here this session. So we'll again meet at 3:40. Oh, 10 minutes. 3:40.